Chinese sodium battery just shocked the EV industry source. Cell Press research published in Cell Reports Physical Science for years. The future of electric vehicles seemed tied to one critical element: lithium. From Tesla's batteries to massive energy storage facilities, lithium-ion technology has dominated the modern battery revolution. But what if one of lithium's biggest competitors has quietly been improving behind the scenes? And what if that competitor just achieved something many experts thought was still years away? A new scientific analysis has revealed that a commercially available Chinese sodium-ion battery performs far better than expected. So well, in fact, that some of its engineering and manufacturing qualities now rival benchmarks associated it. With Tesla's battery technology, the discovery is raising an important question. Could sodium become the next major battery technology capable of challenging lithium's dominance? And if so, how close are we to a future powered by one of the most abundant elements on Earth? To understand why this matters, we first need to understand the problem facing the battery industry. Lithium-ion batteries transformed transportation. They made modern electric vehicles practical. They power smartphones, laptops, renewable energy storage systems, and countless other technologies. But lithium comes with challenges. Mining operations are expensive. Global supplies are concentrated in a relatively small number of regions. Demand continues to rise as electric vehicle adoption accelerates worldwide. As governments and manufacturers race toward electrification, researchers have spent years searching for alternatives that are cheaper, more abundant, and easier to scale. That search has repeatedly led scientists to sodium. Sodium is everywhere. Unlike lithium, which exists in limited deposits, sodium is one of the most abundant elements on Earth. It's found in vast quantities in oceans, minerals, and common industrial materials. In theory, sodium-ion batteries could dramatically reduce raw material costs while making global supply chains more resilient. The challenge has always been performance. Historically, sodium-ion batteries have lagged behind lithium-ion technology in key areas such as energy density and overall efficiency. Most experts viewed sodium batteries as promising, but not yet ready to compete with the best lithium-based systems. That assumption may now need revision. Researchers at RWTH Aachen University in Germany decided to take a close look at a sodium-ion battery manufactured by Chinese company Hein. Rather than relying on marketing claims, they conducted an extensive scientific investigation. The team examined 120 battery cells using advanced diagnostic techniques designed to evaluate manufacturing consistency and internal performance. They tested the batteries across a wide range of temperatures from -20 degrees Celsius to 45 degrees Celsius. They used X-ray imaging to look inside the cells. They disassembled batteries to study electrode structures, materials, and microscopic design details. What they found surprised them. One of the most impressive discoveries involved manufacturing quality. Battery performance depends heavily on consistency. If individual cells vary too much from one another, reliability suffers, and long-term durability becomes more difficult to predict. The researchers found that the sodium-ion cells displayed an unexpectedly high level of uniformity. In simple terms, the batteries were built with remarkable consistency. That level of manufacturing precision is typically associated with far more mature battery technologies. For a relatively young commercial sodium-ion product, the results exceeded expectations. Then came another surprise. The battery incorporated a design feature strongly associated with Tesla's battery architecture. The cells used a tabless current collector design. While the engineering details are complex, the concept is straightforward. Traditional battery cells rely on tabs that collect electrical current from specified locations. A tabless design allows current to flow more evenly throughout the battery. This reduces electrical resistance. It improves thermal management, and it helps maintain more uniform temperatures during operation. These advantages can improve efficiency, performance, and longevity. The researchers noted clear similarities between the sodium-ion battery's architecture and the advanced designs used in Tesla batteries. For many observers, that comparison alone attracted significant attention. Performance testing revealed more encouraging news. The sodium-ion cells demonstrated stronger high-power performance than researchers expected from an early commercial product. The batteries handled demanding operating conditions effectively and maintained solid performance across a broad temperature range. Perhaps most importantly, they showed strong behavior under heavy loads in cold environments. This characteristic could make sodium batteries particularly attractive for energy storage systems and commercial vehicles operating in colder regions. But the story isn't entirely positive. The researchers also identified important limitations. The biggest challenge remains energy density. Energy density determines how much energy a battery can store relative to its size and weight. This is one of the key factors influencing vehicle range. At present, the best lithium-ion batteries still hold significantly more energy than current sodium-ion alternatives. That means electric vehicles using sodium batteries would generally travel shorter distances unless engineers find ways to increase energy density. For many passenger vehicles, that remains a major disadvantage. Another weakness emerged during charging tests. While the batteries performed well in many cold weather situations, charging at low temperatures proved more problematic. Below freezing conditions, charging performance declined noticeably. The researchers believe improved thermal management systems and new operating strategies may help address this issue. But for now, cold weather charging remains one of sodium-ion technology's most significant obstacles. The team also discovered something unexpected inside the battery's chemistry. Certain regions of the cathode contained unusually high concentrations of copper. Even more interesting, the copper was distributed unevenly throughout those areas. Scientists do not yet fully understand what role this copper may play in battery performance, aging, or long-term reliability. It raises new questions that future research will need to investigate. Sometimes scientific breakthroughs create as many mysteries as they solve. This may be one of those cases. Despite these challenges, the broader implications are difficult to ignore. Sodium-ion batteries no longer appear to be merely a laboratory curiosity. They are rapidly evolving into a commercially viable technology. For applications where maximum driving range is less important than cost, durability, and resource availability, sodium could become highly competitive. Grid-scale energy storage is one obvious example. Large battery installations supporting renewable energy often prioritize cost and lifespan over compact size. Commercial vehicles and shorter-range transportation systems could also become strong candidates. Perhaps the most important lesson from this research is how quickly battery technology is evolving. Only a few years ago, many experts viewed sodium-ion batteries as a distant possibility. Today, researchers are comparing aspects of their design and manufacturing quality to some of the most advanced batteries in the world. That does not mean sodium will replace lithium anytime soon. Lithium-ion technology still holds major advantages, but it does suggest that the future of energy storage may be far more diverse than many people expected. Instead of relying on a single battery chemistry, future electric vehicles, power grids, and industrial systems may use multiple technologies optimized for different purposes. The researchers are now focusing on improving temperature charging and increasing energy density. Advances in hard carbon anodes, electrolyte chemistry, and next-generation materials could push sodium-ion performance even further. If those improvements succeed, one of the most abundant elements on Earth may become one of the most important energy technologies of the future. And what began as an overlooked alternative to lithium could eventually become one of the battery industry's biggest success stories.